In the last series of videos, we studied the SIR model, which gave us a bunch of rate equations describing the change in populations between different compartments. And in those equations, we never knew the actual function. So the function remained unknown. And today what we want to do is see if we can somehow approximate that unknown function. And we're going to do that through the use of Euler's method. Euler's method, we have to have a couple conditions met. We first have to have a rate of change equation, and we have to have an initial point. But the idea is that if we increase the independent variable by a small amount, the dependent variable changes by a certain amount too, which we use our rate of change equation for. And then with this, we can scale that by whatever we change in the independent variable, and then we get an approximate result for the dependent variable, in this case the y value. Okay, so let's go through and kind of walk through what Euler's method says. So here's the process. Okay, first thing is we have to have a rate of change equation. Well, in our scenario that's done, and it's also kind of one of the assumptions that we make in using this method. Then we have to have an initial point to start the approximations from. Okay, usually it's given to you. Otherwise, you can determine it graphically or estimate it. And then next you want to determine the change in the independent variable, which we call the step size, and you utilize the formula delta x. Remember delta notation from before, represented a change in the independent variable, or the change in whatever variable, the x variable in this case, and then we divide that by the number of steps. So in the problem setup, it will tell you do this in certain number of steps. And then in the example that follows this, we're going to be doing 3 steps. Okay, and then after this, you're going to use the rate of change equation to determine the change in y prime, or the change in the dependent variable. And then you're going to get an approximation for the dependent variable using y new. So your new value is your old value, so that would be, say, 3 plus whatever your delta y is, whatever you change y by. But now keep in mind this is the instantaneous rate of change, so we do have to multiply by whatever delta x was, and delta x, again, remember, was just this value up here. Okay, and remember from Module 1A that really this step comes from the fact that y prime, the instantaneous rate of change, is equal to the average rate of change on a straight line, and here we're doing straight line approximations, so we're okay. And then you have to repeat 4 and 5 until you arrive at the other side here, so we would stop whenever we get to an x value that has 6 in it, and then lastly make a piecewise linear function using modified point slope form. Okay. Alright, so that's an overview of Euler's method, and really once you get going here, 1, 2, and 3 are all done for you essentially. You have to do a little calculation in 3, but then the main steps is in 4, 5, 6, and 7. Alright, so let's walk through an example. So let's say we have this function over here. We want to approximate it in 3 steps. So that means if I were to compute my delta x, well, I take my final x value, 6 over here. Okay, I can make a little dot there. Okay, so a little dot at 6, and then subtract my initial value of x, 0, and then divide by the number of steps, which is 3, and I get a result of 2. So really what I'm saying is I'm going to have 3 segments in here, and I'm going to step x by 2 each time. So I go from here over to here, and then from 2 over to 4. Okay, and again, so my lines may look something like this. if I were to do a straight line approximation, but this would be a very ideal situation, and we'll see in the end what our piecewise linear function actually ends up looking like. But I'm going to have 3 segments in my piecewise linear function. I need to find these, well, I'm given this point, and I need to find these other 3 points, and then use those points to make a piecewise linear function. Okay, so let's begin the process. Alright, so step 4, we have to start, well, our initial point is given to us, but we use that initial point in our rate equation to determine the change in y. So y prime, and I'm going to say this is for the point 0, 3. Alright, so I have to determine the change in y, and so the change in y is 3/2, and then let's see, I have to insert my 0 plus 1 to the minus 1/2 minus 0.75. Okay, and if I do this computation, I end up just getting 0.75 out. Okay, so my y prime is equal to that, and so my y new is going to be my y old, which was 3, plus, and then remember the equation said it was y prime, so 0.75, times whatever my delta x was, 2. And so doing that computation, I get 4.5. Okay, so this leads, and I'm going to change colors to emphasize this. This means my next point approximation that I get, the y value is 4.5. Okay, simultaneously, remember that I have to step x by 2, so I increase x by 2. So that means the point is 2, 4.5. So if I make a dot at this point, it's going to be up here. Okay, so my first segment should look something like that. And again, it's a little off, and that is perfectly fine. Okay, and we can continue this process by hand, or what I'm going to do now is do this in Excel. Alright, so in Excel, I have my initial point put in. My y prime, I'm just going to enter this rate of change equation. So entering that in, I have equals, I'm going to use 1.5 for 3/2, and then star, parentheses, and then my x value, and I have a t here, same thing, t or x plus 1, and then I raise that to the -1/2 power. And let's see, parentheses are good, subtract off 0.75, and I get the same thing. Okay, and then remember, now I'm at 2, and then I'm going to have that 4 and 6, I'll enter those here too. And then remember, to get my new y value, I do my old y value, and then add on to that the change times whatever my step value is, or my change in the independent variable. All right, and then I can just drag this down to get my change at 2, and then I can just drag this down to complete the table. All right, so that's how you can use Excel to speed up the calculations. Now, and then with this, I can now form the piecewise linear function. Okay, here I do want to make some connections. All right, I want to specifically highlight the slopes, and I want to identify these points. Okay, so if I look in my Excel table, okay, I'm going to look at my Excel table. Remember, this is the slopes, the y prime values. So I'm going to look here. Okay, 0.75, 0.75, 1.116. Okay, so essentially all the slopes I can read off right here. Remember, y prime means the rate of change in y, the instantaneous rate of change in y with respect to my independent variable, so x and not t here. So I can actually just form my piecewise linear function by reading off these values right here. And then these are just the y values at the corresponding points. So whenever x is 0, that's the y value. X is 2, that's the y value. And those are all there for me too. Okay, so it's relatively easy to make a piecewise linear function if you have the Excel table handy. Alright, and then lastly, so that's the end of the problem. But if I just wanted to graph this and show you, remember the blue function is what we started out with. That was our exact function that is being graphed. And then if you graph these these lines, the piecewise linear function for 3 segments, again, we're using a subscript of 3 to denote how many pieces we have, or how many steps we did. And so that ends up being the line in red. So we're off significantly, but we can still have an estimate of the y of x function. In the next video, we'll look at improving this estimate.